everyone, what's up? Welcome back to my tutorial channel. Daniel's here, and today I'm gonna talk about part 4 of topic 6, the normal approximation to binomial distribution. And in this part, I'm gonna first review the binomial distribution, then I'm gonna show you how to approximate binomial probability using the normal curve. So first, review binomial distribution. Remember in topic 5, we learned that there are certain conditions for a random variable to follow binomial distribution. The first condition is a fixed number of trials are conducted. Number 2, there are 2 possible outcomes for a trial. One is labeled success and the other is fail. Number 3, the probability of success is the same on each trial. Number 4, the trials are independent. This means that the outcome of one trial does not affect the outcomes of the other trials. Number 5, the random variable x represents the number of successes that occur. And we have some common use notation. The number of trials is usually denoted by n, and the probability of success is denoted by p, and of course the probability of failure is 1 subtract p. The mean of binomial random variable is mu of x is n times p. The variance is sigma squared of x is equal to np 1 minus p, and the standard deviation is just the square root of the variance. Now we go to the main objective of today, how to approximate binomial probabilities using the normal curve. Remember, in topic 5, we learned about how to compute the binomial probability exactly. So why do we have to learn how to approximate the binomial probability instead of computing exactly in this lesson? Sometimes binomial probabilities can be very difficult to compute exactly by hand because many terms have to be calculated and added together. For example, if we consider a coin that is tossed 2,000 times and we want to find the probability that the number of heads is between 75 and 1250, then there should be 1,075 terms to be calculated and added. This work is nearly impossible without technologies. So the idea is we think about how to approximate the probability without calculating so many terms. So we think about the central limit theorem for proportion. Remember, the central limit theorem for proportion say that if np is at least 10 and n1 minus p is also at least 10, the sample proportion p hat is approximately normal. And we know that x is basically n times p hat, where x is a binomial random variable representing the number of successes. So basically x is just a constant times the random variable p hat, where p hat is approximately normal. So of course x should be also approximately normal. So the normal approximation to binomials say that let x be a binomial random variable with n trials and success probability p. If np is at least 10 and n times 1 minus p is also at least 10, then x is approximately normal with the mean mu of x is n times p, and the standard deviation square root of np 1 minus p. Let's consider this example. Let x follow binomial of 1,000 and 0.3. That means the number of trials is 1,000 and the success probability p is 0.3. So x is approximately normal with mean 300 and standard deviation 14.49 because 1,000 times 0.3 is greater than 10 and 1,000 times 0.7 is also greater than 10. Here we are going to compute the probability that x is less than or equal to 300 by two methods, by exact methods and by approximation method. By the exact methods that we learned in topic 5, the probability that x is less than or equal to 300 is 0.5156, and by normal distribution, the z-score of 300 is 0 because 300 subtract 300 over 14.49 is 0. And the area to the left of 0 under the standard normal curve is 0.5. And you see that these two values are not precise. The approximation is not precise. The reason is binomial distribution is a discrete distribution, while normal distribution is continuous. So when we approximate the binomial distribution using normal, the answer usually is not precise. And to get rid of that resistance, we use a method called continuity correction. The continuity correction is an adjustment made when approximating a discrete distribution with a continuous one that can improve the accuracy of the approximation. To see how continuity correction works, let's consider this example. Let x represent the number of heads. Then x has the binomial distribution with n is 100 trials and success probability p is 0.5. Imagine that we want to compute the probability that x is between 45 and 55. This probability will differ depending on whether the endpoints 45 and 55 are included or excluded. And to get the best approximation, we should compute the area under the normal curve between 44.5 and 55.5. Let's look at this histogram. The histogram is using binomial distribution. And to compute the probability between that is x between 45 and 55, we basically add in these rectangles. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 rectangles, the shaded rectangles. However, if we use the normal curve and if we compute the area from 45 to 55, we have half of the first rectangles and half of the second rectangles. So when we add them together, we basically have only 10 rectangles instead of 11. That's the reason why without continuity correction, the probability, the approximation probability tend to be incorrect. So to get rid of the incorrection, we extend the rectangles, the intervals. So we subtract 0.5 to 45 from 45 and we add 0.5 from 55. So the new interval is from 44.5 to 55.5. The new interval cover the old interval. So usually by continuity correction, the new interval usually should cover the old interval. So here is how the continuity correction works. Following are the areas under the normal curve to use when the continuity correction is applied. If the question asks for the probability that x is a is less than or equal to x less than or equal to b, then we can approximate this probability by using the area under the normal curve between a minus 0.5 and b plus 0.5, because we want both a and b to be included. The probability that a is strictly less than x and strictly less than b is the area under the normal curve between a plus 0.5 and b minus 0.5, because we don't want to include a and b. The probability that x is less than or equal to a is the area under the normal curve to the left of a plus 0.5, because we want a to be included, so we make the upper limit to be a plus 0.5. If the question asks for the probability that x is strictly less than a, we can approximate it by the area under the normal curve to the left of a minus 0.5, because we don't want the endpoint a to be included. If the question asks for the probability that x is exactly a, then it can be approximated by the area under the normal curve between a subtract 0.5 and a plus 0.5. This is a clear example to see that continuity correction is important. Without continuity correction, probability x equal to a using binomial distribution is not zero. However, if we don't use continuity correction, probability that x equal to a using normal distribution is zero, because for continuous distribution, probability at any single point is zero. Next, probability that x is strictly greater than a is approximated by the area under the normal curve to the left of a plus 0.5, and the probability that x is greater or equal to a is the area under the normal curve to the left of a minus 0.5. So that's how the continuity correction works. Now let's take a look at the procedure how to approximate binomial probability using normal approximation. There are 5 steps to approximate binomial probabilities using normal approximation. The first step, we have to check to see if central limit theorem is applicable. So we have to check 2 conditions. NP is at least 10 and n times 1 minus p is also at least 10. If both are met, it is appropriate to use the normal approximation. Otherwise, the probability must be calculated with the binomial distribution. Step 2, once the 2 conditions in step 1 are both met, we can compute the mean and the standard deviation of variable x. Then step 3, we use continuity correction. That means we have to determine whether to add 0.5 or subtract 0.5. Step 4, we sketch a normal curve, label the endpoints, and shade in the area to be found. And step 5, we use table A2 or technology to compute the area to the left or to the right depending on the question. And note that if you are allowed to use technologies, usually if you are using technology, you may be able to compute the probability exactly without using normal approximation. So the normal approximation is good when you're not allowed to use technology. You have to compute by hand. So now let's do one example. The statistical abstract of the United States reported that 66% of students who graduated from high school in a recent year enrolled in college. 100 high school graduates are sampled. Let X be the number who enrolled in college. Find probability that X is less than or equal to 75. So here, the first step we have to verify if central limit theorem is applicable. That means to see if the normal approximation is appropriate. Here n times p is 100 times 0.66, which is 66, is greater than 10. And n times 1 minus p is 34, which is also greater than 10. So the normal approximation is appropriate. In step 2, we compute the mean and the standard deviation using the formulas. Step 3, since we want to find the probability that X is less than or equal to 75, we want to include the point 75 in the calculation. So we find the area to the left of 75.5. The area to the left of 75.5 does include 75. Now we find the z-score of 75.5. So the z-score is just x minus mu over sigma. So we take 75.5, subtract 66, and take the whole thing divided by 4.74. So the z-score of 75.5 is 2.01. And step 5, we can find the area to the left of the z-score of 2.01, and we can use the A2 table. It should be 0.9778. So 2.01, we look for the row of 2.00 and the column of 0.01. And here's how the picture looks like. 75.5, the area to the left is shaded in the blue color, and the z-score of 75.5 is 2.01. So that's all for today. Thank you so much for watching my video. I hope you find my video helpful, and see you next time. Bye.